In this voiceover, we continue our discussion of enzyme kinetics. We saw how to set up an experiment to measure enzyme kinetics, and then the curves shown here again that describe the reaction rates for the conversion of substrate to product in the reaction E plus S goes to E plus P. We also saw that at concentrations greater in this case than 4 times 10 to the minus 5th molar, the enzyme became saturated with substrate and the enzyme reaction could not proceed any faster. In the next step, we're going to determine the initial reaction rate at each substrate concentration by finding the slope of each curve near the beginning of the reactions, as shown here. The slope of each curve, the rise over run, is in fact the initial reaction rate. In other words, amount of product formed per unit time at the very start of each of these reactions. The next thing we'll do is plot those slopes, or V0 meaning the initial reaction rate, versus the substrate concentration that gave that initial reaction rate, and here's the curve you would get. The curve is approaching a maximum asymptotically. You may remember that term from some math course you've had. In fact, the curve is a regular curve, in this case, the rectangular hyperbola with the general equation y equals xa divided by x plus b. You can look that up in a math textbook that you may have used in another course. This is classic Michaelis-Menten kinetics, typical of many catalyzed biochemical reactions, named after the biochemists who derived the actual equation for the kinetics. The equation for this curve follows the formula of that for a rectangular hyperbola and is the initial velocity, or V0, equals Vmax times the substrate concentration divided by something called Km plus the substrate concentration. So now let's talk a little bit about Vmax and Km. Here's our graph again. Here's Vmax, that asymptotic approach to a maximal rate of reaction. And here's Km at the bottom of the graph. Km turns out to be equal to the substrate concentration at which the reaction is proceeding at 1/2 of its maximal velocity, or maximal rate. So Vmax is the maximum rate of catalysis by an enzyme. It is attained, in fact, when the enzyme is saturated with substrate. Let's look at this biochemical pathway in which A is ultimately converted to E. It's catalyzed by a series of enzymes, E1, E2, and so on. Let's ask, assuming that the concentration of A is not limited, that is, it's abundant, how fast will product E be made? Only as fast as the slowest or rate-limiting reaction in the pathway. It's a bit like the weakest link in a chain analogy, isn't it? What about Km? Km is the measure of the attraction of E for S. We say the affinity of enzyme for substrate. Let's look and see why this is so. Km, remember, is equal to the substrate concentration at 1/2 Vmax. So for a reaction with a high Km, what that means is it will take a high concentration of substrate to bind half of the enzyme molecules, won't it? You need more substrate, in other words, to achieve half Vmax and therefore also Vmax, the maximum catalytic rate. You can rewrite the equation for the formation of the enzyme substrate complex this way. E plus S goes to ES, but the reactants seem to be favored. In other words, it is less likely to form an ES complex if the Km for the reaction is very high. What about a reaction with a low Km? Well, think about it for a minute. It means that it only takes a low substrate concentration, does not take many substrate molecules to bind half of the enzyme molecules. In other words, you need less substrate for this reaction to reach Vmax. We could write the formation of enzyme substrate complex then maybe this way. The formation of the enzyme substrate complex is perhaps more favorable for a reaction with a very low Km. Km is actually a dissociation constant. It's a measure of how likely E and S are to remain apart, which means that the reciprocal of Km, or 1/Km, is a measure of how attractive E and S are for one another. Under the right conditions, 1/Km is generally thought of as an affinity constant. It's actually a measure of how likely it is for enzyme and substrate to come together. So the higher the Ka, the stronger the affinity. The higher the Km, the more likely E and S are to remain apart or to dissociate. Rate-limiting reactions in a biochemical pathway are typically and often regulated. Why would they be regulated? Because they're rate-limiting. If you want to make more final product, in the example in the previous slide, to make more E, you would have to increase the rate of the rate-limiting reaction. You could do this by increasing its Vmax. You could do it by increasing the affinity of the enzyme for its substrate, in other words, lowering the Km, or both. And we saw that enzymes are indeed regulated by changing their shape, by allosteric regulation. We're going to look in the next few presentations at glycolysis, and we're going to use glycolysis to illustrate some real-life bioenergetics examples. We're going to discuss the role of coupled reactions in making energetically unfavorable reactions proceed. We're going to look at something called substrate-level ATP production. We're going to briefly look at a few enzymes by name and try to understand why they were called what they are called. We are going to see some real-life examples of allosteric regulation and also an example of something that I call genetic regulation. And we're going to look at biologically irreversible reactions and their implications. I'll only tell you now that since all chemical reactions are thought of as inherently reversible, we're going to need to understand what a biologically irreversible reaction is. And that brings us to the end of this voiceover.